Testing. Hi there. Hi there. Just checking the music. Just checking the music. Oh shit. Hi there. Testing, testing. Hi there. Testing 1, 2, 3. I guess that's good enough. Hi there, everyone. I'm Cookie, and well, I guess so far I've only done gaming on this stream, but I actually have a background in engineering, believe it or not. I kind of want to get into it more, so I thought I'd just go back and rehearse everything that I used to know to a degree. Today I was just doing projectile motion. It's pretty simple. Okay, maybe I shouldn't start with that. I don't know what else to say. I guess we'll just get into it. I have a PDF I found online, so okay, I guess projectile motion are objects launched at an angle with respect to a horizontal surface. It looks like here they have V0, which is the, I guess, V0. It's also called V0, which is just the velocity of the object is going this way. And then they have Vy, V0Y, and V0X. I guess V0 to begin with is like the initial point of velocity, so there will be like a velocity here or here on the path, but V0 is specifically where it originates. So V0 is just that. V0 X and Y, those are like how do I describe it? That is the initial velocity in the x direction and the y. So the directions, x is horizontal, y is vertical, up and downy. Theta, that's just the angle from the x-axis to v0, and theta's the angle, which is that symbol. And then here we have what these equal. They all have values, which is just v0, the main thing, cosine or sine of that. And you may have learned about the here, let me draw it. This one's pretty simple. 1, 2, 3. Sine, cosine. I haven't done this in a while myself. So that's theta sine vy. V naught y equals the main value here, which is v naught y, which equals v naught sine theta. You've seen this. This is what I was trying to refer to. Can I not bring this down? Oh, I can't. It's just goofy. And let me do that. Knock, knock. Let me back in. Doo-doo cam. There we are. Yeah. Alright, so yeah, we have a it's basically just a triangle. Use the value of this, the hypotenuse or whatever, times sine theta, which is what's happening here, to get the this value, which in this case is v naught y, and we have v naught x, which equals the hypotenuse length, aka v naught, times cosine theta. Yeah, that looks good. Okay, and then that arc nonsense, creating projectile motion. Throw a ball straight up while moving on rollerblades. As long as you do not change your speed or direction while the ball is in flight, it will land back in your hands. They're just saying there's no Vx. As long as you do not change your speed or direction while the ball is in flight, it will land back in your hands. Yeah. Yep. And then while moving, you throw your ball straight up and relative to yourself. Notice that the ball is always above your head. Oh, in this case, they're just saying as this person moves, the ball, like when the ball was in their hands, it had the same x velocity as them because they're on rollerblades moving. So when it goes up, the Vy is changed because now it's moving, and then because of gravity, it'll come back down. That all affects Vy. Gravity doesn't affect Vx because gravity doesn't affect left and right. So it comes back down. If you did this in real life, or at least high enough or windy enough or whatever, it wouldn't be like this because wind would slow down the ball in the air, so it'd probably land behind you. But whatever. Yeah, okay. Qualitative analysis of projectile motion in the Y. A ball thrown straight up in the air by a person moving horizontally on rollerblades. In this case, they're obviously like a lot of basic engineering, or I guess physics problems don't include stuff for the sake of learning, like what the frick, like wind, Jesus, stuff like that. Okay, ball thrown straight up in the air by a person moving horizontally on rollerblades. Earth exerts a gravitational force on the ball, so its upward speed decreases until it stops at the highest point, and then its downward speed increases until it returns to your hands. With respect to you on the rollerblades, the ball simply moves up and down. Oh. With respect is like, here, relative to us, like perceiving this event, they're both, the ball's going up, she's going this way. Okay, how would I describe? Okay, y, the velocity in the y direction, up and down. We can see that the ball is moving up and down while she's just not moving any direction y. In the Vx, we see them both moving at an equal speed. What it means by relative is, for the woman, the ball is always above her, like always, in any time in this situation. Yeah, like I don't know. Vx doesn't change when you're looking at both of them. Like, from her to the ball in the x, left and right, is always just right above. Okay, Earth exerts that with respect to the rollerblades, qualitative analysis of projectile motion, the x-axis. A ball thrown straight up in the air by a person moving horizontally, and rollerblades will land back in the person's hand. The ball will move horizontally. Yeah. No objects exert a horizontal force on the ball. Thus, according to Newton's first law, the ball's horizontal velocity does not change. No object exerts, except for wind resistance, but whatever. The ball is horizontal, yeah. Yeah, they're just saying, like, what they're doing in their situation is, let's say we had, the person, no boy. Here's a human, and here is El Ballet. There. Currently, her velocity, or I guess we want to look at forces. Forces, there's gravity, which is down, gravity, but she's on the ground, so it doesn't really do anything. Same here, gravity, that's why it goes in a curve. It has velocity up, but slowing down in the upwards direction because of gravity, which eventually becomes negative and comes back down. And if you're ignoring the force of air or wind or whatever, wow, I lost focus. Come on. There. If you ignore the force of air, so that doesn't exist, there's no forces acting on this except gravity. So in the x direction, the whole situation, it doesn't change. They're both going to go this way because nothing is slowing either. Wind resistance for her too. Like, if you were rollerblading in real life, you would slow down at some point. Not her case. She'll go for forever. Yeah. No object exerts horizontal, according to first law. Okay. Oh, I might as well say this. I don't think they're here, but thank you, baby Alex, for following me, even though I wasn't live at the time. Or I was, but it was starting soon. Okay. Qualitative analysis of projectile motion in the x and y axes. A ball thrown straight up in the air by a person moving horizontally on rollerblades will land. Yep, we already discussed that. The ball continues moving horizontally as if it were not thrown upward. Yeah, they're just saying the y force doesn't affect the x force. The ball moves up and down as if it, it seems the horizontal and vertical motions of the ball are independent. We need to test this pattern. Okay, I don't think I'll be doing this. Let me just say. Testing experiment. One ball is shot horizontal. Oh yeah, they did this in high school when I was in that place. Okay, experiment test independence of, So this is one method they use, a very simple way of testing the relation between x and y, which is not. Test experiment. One ball is shot horizontally with a compressed spring is released, this one, and simultaneously a second ball is dropped. Which ball hits the surface force first? So basically, time for a drawing. We have two balls. We have we have two balls. Here's ball one, or I guess ball two from how they described it. It will fall down, so it only has gravity affecting it. So it'll be released into space, open space, like there's nothing affecting it, like no ground or anything. And it'll just fall because of gravity. And we have we have the other ball. It's basically identical. Gravity is still affecting it. Gravity. And however, we have another force acting completely in the x direction, which is the force caused by the spring. Okay, so these two forces. So they're saying we have in the x a force and spring in this one, nothing affecting this one, and we have gravity affecting both of them. And basically, you're going to see which one lands first. While normally it would be understandable to think it might be different based off like the forces affecting it, it makes sense it would be the same because the only thing affecting up and down, the y, is gravity, and they're the same. They're identical balls. So, okay, prediction. Both balls start with 0 initial vertical speed, thus their vertical motions are identical. Since we think that the vertical motion is independent of the horizontal motion, we predict that they will land at the same time. That is, yeah. And then the outcome, they do in fact land at the same time. So, science is in fact correct. Okay, the outcome supports independent... so the conclusion is the idea of independent horizontal and vertical motions. We failed to disprove this idea. The idea is correct. They're independent, as of this example. Okay, conceptual. Throwing a ball. You throw a tennis ball as a projectile. Oh boy, let me check something. My computer does not look happy at me. Why are you mad at me? Oh, it's got 43%. I should have it charged, especially since I'm streaming, but I didn't want to get my charger. So, oh boy. Anyways, conceptual exercise. Throwing a ball. You throw a tennis ball as a projectile. Arrows represent the ball's instantaneous velocity and acceleration, and the force or You throw a tennis ball as a projectile. Yeah. Arrows represent the ball's instantaneous velocity and acceleration, and the forces or force exerted on the ball by other objects when at the three positions shown in the diagram. So first, we have, and you can see how velocity changes. Actively, at this exact moment, it's going that way. At this moment, it's going straight. Because, like, this is the exact moment where, how do I describe this? So, right, okay. There. Alright, so if we look at a arc, I guess, here, this is the path to travel. Right before this moment, the velocity is like this. Before it was like this. So as you can see, it's like getting flatter as it goes. That's because the y direction velocity, like this, when it initially starts, it's like, this is Vy. Vy is decreasing. Vx is the same. We're not worrying about that because there's no force effect. Vy is decreasing. The reason for that is gravity, which is a force, and force equals mass times acceleration. Is that what I wanted to explain? No, mass times gravity is the gravity one. What is my point? forces affect velocity. There's a constant one pulling down, so the velocity in the y is slowly decreasing. And once we get after that, like down here, it'll be like getting more down or whatever. Like it's getting more negative. That's like the ball will keep speeding up going down until it reaches terminal velocity. But at one point, it has to cross from going up to going down. That's this middle section where it's going exactly straight, which is what they're showing. Okay. Let's see. Vy is a combination of Vx and Vy, which is changed. Yeah, see, they say constant Vx because nothing's affecting it, and changing Vy because it is in fact changing. Oh, yeah, they pointed out pretty exactly the same. It's going up, straight, and then it points down. And oh, you can see Vx is the same in all of these cases. Unlike Vy, no Vy, and Vy is down. That's... Oh, yeah, and here's the forces. Velocity, velocity, velocity. That's not force. These are the force things. What? I don't know why there's two force. Oh, they're just listing all three. There's velocity, force, and acceleration. The velocity is changing throughout the process because of force, and that force is giving it an acceleration. The acceleration is the gravity constant, which is like 9.81. That's like how much, I don't even know. Doesn't matter, whatever. The point is there's a constant force due to gravity. And it changes, that's how it affects it. It's arc. Okay. Quantitative analysis of projectile motion acceleration. The equation of motion for velocity and constant acceleration are used to analyze projectile motion quantitatively. The x component in the horizontal direction, yep. The projectile acceleration is 0. The x component in the horizontal, yep. And the y is the constant I was talking about, which is projectile's acceleration, which is negative g. The reason they're saying negative, how do I want to describe this? Okay, so when you're doing complicated mathy gimbo combo, they kind of like have a axis. So in the case of a 2D one, there's like x and y, which we've been dealing with. X is pointing in the positive direction and y is pointing in the positive direction. So when gravity in this case is pointing opposite of y, gravity, we list the value of this variable is negative. Or you could do negative g. It depends on how you want to do it. It's basically just going to be you can have it as g equals negative 9.81, which in hindsight that's probably a better way of doing it, the way they're doing it. Or you could do negative g. No, you wouldn't do that. Yeah, you do this. This makes sense. Because it would be this. So we have g equals negative 9.81, and then y hat. The hat this is just a determines the direction. So the value by itself is 9.81. That's the value g, and we multiply that by the direction, which is y hat. I just have 1 there because that's how it's done. Yeah, so 9.81. Oh, sorry, it's negative because it's not pointing at y, it's pointing at negative y. So we have the value, and then we have the direction, which is negative y, which equals negative 9.81. So that's a little overcomplicated for what's needed right now, obviously. Like, you probably won't ever see y hats and goo goo gaga, but you know. Okay, did I draw on myself? Please tell me I didn't. Good. Okay. The force is I did write this earlier. The force is mg, the force of gravity of Earth exerts on a projectile. So, gravity Gravity is an acceleration. Okay. So gravity is a type of acceleration. The traditional equation is force equals mass times acceleration, and when it comes to gravity, we write force equals mass times gravity. So in that sense, the higher the mass is, okay, so G is always going to be 9.81. That's always the acceleration caused by gravity. However, the heavier an object is, the more mass it has, the larger the force that gravity puts upon a body. So that's why something that's heavier could fall faster. Yeah, stuff like that. Just more force is applied to that object. Okay, more goo goo gaga. Quantitative analysis of projectile motion velocity. How many pages are in this thing? I've gone through a lot of them. Quantitative analysis of projectile motion velocity. For a projectile launched at the speed v0 and angle theta with respect to the horizontal axis. When they say respect to, again, it's just like they're saying you could basically ignore that, but they're saying with respect to the Earth, basically, like your plane of seeing things. You can see it like this. Like if you were to say with respect to the ball, where does the ball move? That would be 0 because the ball doesn't move to itself. If you said to the sun, like if you were on the sun and you were watching how the ball moved, obviously it's moving ridiculously because it's following the orbit of Earth and the Earth spinning and blah 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 blah. But we're just looking at the respect of the axis or the plane of our little world here, which does not move. For a projectile launched at the speed v0 at the angle theta with respect to the horizontal axis, we have all this jazz. Its initial x y velocity components are v0 x. Yep. Oh, this was the beginning. The x component of the velocity remains constant because nothing's affecting it, because the acceleration is 0 in the x direction. No positive or no negative. That's good. Okay. Quantitative analysis of projectile motion using kinematic equations. Projectile motion in the x direction. Oh, hold on. Acceleration equals 0. Yeah, we already know that. Because no force affected, Vx equals V0. Oh, so they're just saying it's constant, so it never changes. Okay, that was weird. Sorry, I just got a message. Motion, Ax equals not, that equals that. Oh, right, because, yeah, that's the equation for V0 x, which equals that. X equals x naught plus... Okay, so this is just a equation for the position, how much distance it's traveled. So the position of x equals the initial point where we started. So it could be we started 0, or say you started like 5 meters away. You'd start from there and add on, like, this is just where you start. And then we have what's gained through the projectile travel, which is v0, our initial velocity, times cosine theta times t. How would I describe that? Yes. Okay. Right. So how that works is the equation is I guess I should finish describing x naught equals, am I already on the mire? I better not be. I might be. Which equals x naught, which is the initial, plus this equals that basically. So v0 x equals v0 cos. Yeah, okay, so that's the same thing. Let me write that quickly. X equals x naught plus v naught xt, which equals x naught plus v naught cosine theta t. So you can see the similarity. V naught x equals v naught cosine theta. How to make sense of this is, let's start with the x naught thing, though this is kind of simple. Say this was our starting point. So here, this is where x equals 0, right? So if you start here, x equals 0, or x naught. If you start, let's say here, 1, 2, 3, x naught would equal 3. It depends on where you start from. Like your arc would go off like this or go off like that. Yeah, you need to include your starting position corresponding to where your reference is, your reference point, origin, which is like this. Yeah. Okay, so that's what x naught is. And then we have the more complicated jazz, which is v naught x t, which is just the velocity in the x direction initially. You can calculate it with constant, but since v naught x is constant in this case, that's great. There are times, obviously, like with wind resistance, where that velocity will change, and that gets a lot more complicated because you have to consider all the velocities, which includes, you basically use acceleration to help you determine the distance traveled in that case, but I'm getting ahead of myself. Here we have v naught x t. Basically, you can break it down by units. That's one way of looking at it. So velocity, one example is meters per second. That's a way of measuring velocity, and a measurement of time is seconds. So we have meters a second multiplied by seconds. That equals meters. That's just one way of seeing that multiplying these two will get you a distance traveled set. And a way of looking at like physically in the real world would be, yeah, let's do it this way, I guess. Alright, so here's our initial start point. I'm just gonna say it's 0. We travel here. Alright, so when you're looking at the distance traveled, you do not need to consider the y velocity, because that's just how much is traveling up and down. You need the vx, because that's how fast it'll move across this. The only other thing you need is time, how much time it's traveling, which is basically when it stops moving, which is the contact point from when it's traveling to the ground. So, I mean, yeah, that time is obviously determinant on Vy because of how much airtime it has before falling. But yeah, I don't know what else to say. The distance traveled will always be based off Vx. It could travel up for you could travel 1,000 meters into the sky, but if its Vx is like it's tiny, it'll still fall like really close to this, or if it's 0, it'll just fall straight back down right here. Yeah. So, and yeah, a velocity times time is the distance traveled during that time. So, you could even consider it without the air time. You could just be like, a person here is walking. That's a person. Okay, well, fine. A person is walking a speed of 5 meters a second for 10 seconds. And how far do they travel? 5 meters a second time. Just realized how ridiculous this is. Equals 50 meters. Yeah. So if they were traveling 5 meters a second for 10 seconds, it'd be 50 meters. It's like that, basically. It's the same thing, except that there's a movement up and down, but in this case, it doesn't really affect the distance. You just need Vx. Okay, wow, that was a tangent. And my computer is very close to dying. I should get the charger, but I don't wanna. The y equations can be determined, can be used to determine the time interval. The x can, oh, so yeah, and then there's the y ones, which I'll cover, but they say here what I kind of explained for x. The y equations can be used to determine the time interval for the projectile's flight, so that's how long it's in the air. And the time interval is what you need anyways for this one. The one thing x and y have in common here is time. Those are the same for both of them. Anyways, the x equations can be used to determine how far the projectile travels in the horizontal direction during the time interval. So yeah, it's kind of the steps how you work a problem out. You have the y equation, and you can use it to get time interval, and then using time interval you get how far you travel. And here we have the equation. That's our acceleration. Velocity y equals the initial velocity plus how it's changing with time. The longer the time goes, the more it's affected. And I can show that quickly. Let's see. Oh boy, I've been writing upside down this whole time. Oh well. I'll fix that next time. Okay, so how do I want to describe it? AY equals negative g, which equals negative 9.81 meters per second squared. Acceleration, its units of measurement are meters per second squared. Yeah, so in the case of the equation Vy equals V naught y plus AYT, we have the units meters per second, equals meters per second, that's the initial velocity, plus the change, which is the acceleration, which is meters per second squared, times time, which is seconds. Wow, I'm an artist. Okay, there. Seconds. Okay, and if you do that, you can see that we have meters per second squared times time. That would equal meters per second, which is the velocity. If I actually plugged in this value, the negative 9.81, this would be a negative value that increases with time. So like at 1 second it's negative 9.81 the velocity, and then at 2 it'd be like double. And that's kind of how it becomes. Like, say this was 20 initially, so we'd have 20 plus a negative number, and that negative number gets bigger over time, and that'll keep happening till it finally hits the ground and can't move down anymore. Vy, V9, y equals, and this is the equation for y equals y naught. Initial position, the y. Vyt. I'm tired. V initial y times time. Why not? That's the initial position y. And that's the change plus and then it just, so this is like using the initial velocity of y in the y direction times time. That would be like a ridiculous number that is incorrect, but this fixes that. So we're gonna have like a large positive number going up because it's like unstoppable, and then we have the acceleration that's going to bring it down. So 1/2 acceleration, which is a negative, and time, which is positive. This will just be a negative times squared. Yeah, you can see that would kind of get high pretty quickly. And they're just saying this is another way of stating it. That's the Vy, not y. And then, see here they replaced AY with gravity. Boop. Okay. Oh man. 29%. Oh, we're at examples. Is this all examples? Yes, it is. Best angle for farthest flight. Alright, I'm gonna deal with that tomorrow because, or I guess not tomorrow, it'd probably be Wednesday. I kind of just wanted to test how this setup works because I had to like move my computer and I have like all my other jazz. The iPad 2. This is a iPad Mini 2 from like the ancient era. So yeah, old tech. It doesn't have much uses, but I guess as a PDF reader or PDF just like device, it's pretty handy, especially for stream. But yeah, I'm happy with how things work. I have this, and what I planned on doing, I have this fancy little thing. It's a Kokio right here. Kokio. aka Campus notebook binder. It's only this big. It's really tiny. That's not a good representation. There. Pencil here and blah. It's like it's small and it fits the paper. So point proof. But it's a binder, which I love. Because I like reorganizing my notes and stuff. So this works great. I took all the paper out, and I'm just going to put paper in whenever I do this stuff. So that should go fine. There, in my head at least. Okay, I see what I did wrong. There. And there we are. Is that the right piece of paper? Yeah, it is. Alright, so one piece of paper, a lot more to go. Cool. Okay. Happy with how that went. Thank you for the follow, baby Alex, and anyone who sees this. And have a good day. Bye.